Okay. So in any case, now we're going to go ahead and cover Coulomb's law. And let me pull this a little bit closer so that everything's visible. Okay. So now Coulomb's law has to do with how charges affect each other. Charges can exert forces on each other, and Coulomb really played on an earlier law that had been created by Newton to describe the forces that masses exert on each other due to gravitational attraction. Coulomb tried this on charges, and it starts out with an image, a little picture. Okay, so we've got two objects in the picture. This is Q1, and this is Q2. Okay, Q is a symbol used to represent electric charge, and these two charges have values Q1 and Q2, and we can plug numbers into that later and see how much force is exerted between them. And let's say the separation distance is r, some radial distance. And let's consider this to be an attractive force. So we'll draw arrows connected to the two objects, and the arrows show the direction of the force that's being exerted between them. And this will be Fe. And right now we're not going to worry about the vector nature of it, so I'm not drawing vector symbols over the top. But those are going to be equal and opposite forces. Thing one is exerting a force on thing two. Thing two is exerting a force back on thing one. So this is a gravitational, an electrical attraction. And so this image goes with Coulomb's law. And now Coulomb's law says this, basically, that the electric force, lowercase e here, subscripted capital E here represents the electric force, and that's going to be equal to 1 over 4 pi epsilon sub 0. So this ratio, this is a constant, we'll talk about epsilon sub 0 in a minute, times Q1 times Q2 divided by R squared. Now this is the magnitude of the electric force between these two charges, Q1 and Q2. In order to be able to determine what the actual value is, you need the value of Q1 and Q2, obviously, and now the units are going to be coulombs again. And you'll need this distance, R, which of course is going to be in meters. So what we've got here is an equation that describes the force, this 1 over 4 pi epsilon sub 0. This is a constant value. I'll give you the value of it in a minute. And Q1 and Q2 are charges, the two charges that are exerting forces on each other, and R is their separation distance. So let's see, let's give you the value of 1 over 4 pi epsilon sub 0 first. So it's approximately equal to 9 times 10 to the 9th newtons meters squared per coulomb squared. Capital C is used to represent coulombs, so these units are very strange, but they're the units that are necessary that you plug in here. You've got coulomb squared up top. In this part of this ratio, you've got meters squared on the bottom of that ratio. So notice you've got meters squared up top in the units associated with 1 over 4 pi epsilon sub 0. By the way, this is called either Coulomb's constant or the electrostatic constant. And it kind of helps describe the force or the size of the electric force between charges. Now, this is going to be a very important quantity that we're going to use over and over and over again throughout this chapter, well, certainly throughout this chapter, but also throughout the entire course. So you'll need to become familiar with that. And then epsilon's of zero, permittivity of free space, which is basically a quantity that describes the how easy it is to exert force, electric force from one charge to another through empty space. And it's equal to 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. This is one of those physical quantities that is it's not derived, it was measured, and it describes the size of the force between charges. Now, I'm going to go ahead and use this equation to determine the force between two charges that are all arbitrarily picked here. So let's say we've got a charge here. Let's say it's negative 1.5 times 10 to the negative 12 coulombs of charge. And then over here, I'll have a positive charge. So this is filled in. And so this is a negative charge, and we'll call this Q1. And then over here, this is Q2. I'll leave this open. This will be Q2, and Q2 will be equal to, let's say, 1.5 times 10 to the negative 12 coulombs again. Now, notice this one's positive, this one's negative. So remember, you can have positive or negative charge. So now, unlike charges, negative and a positive, unlike charges attract. So now this is going to be an attractive force. Remember, like charges repel, unlikes attract. So in order to show that electrical attraction, you draw arrows coming from the two objects toward each other, so that it represents an attractive force. And this is going to be the electric force. Now it's just going to be the same amount of electric force from one to the other. So let's go ahead and solve for this electric force. But first of all, let's give a distance. So let's say that the separation distance between these two charges equal and opposite charges of 1.5 times 10 to the minus 12 coulombs. Let's say R is equal to 0.03 meters, so 3 centimeters. So these small charges are 3 centimeters apart. We're going to determine what the electric force is between them. And by the way, it's not uncommon for objects to pick up this amount of charge on relatively small objects, and this distance is roughly an inch. So this would not be an uncommon kind of value to see in a lab where you were putting charges on objects and trying to determine the force between them. So let's see. So this electric force now is going to be equal to, well, the 1 over 4 pi epsilon sub 0 always needs to be there. We know that its value is 9 times 10 to the 9th newtons meters squared per coulomb squared. Now we'll multiply that by the two charges multiplied together. And they're both the same size charge, so I'm just going to put 1.5 times 10 to the negative 12 coulombs. Now I'm going to square that, and I'll put a negative sign out front because remember, one of these terms is negative, or one of these factors is negative. Then we're going to divide by 0.03 meters, so that'll be 3 times 10 to the negative 2 meters, and that needs to be squared. So let's look at the units first. Coulomb squared, cancel with these coulombs squared. That's good. Meters squared, cancel with these meters squared. That's good. And that leaves nothing but newtons. That's great because should be newton, should be a force unit. Let's see. Okay, 3 squared is 9. This 3 has to be squared. And we've got a 9 up here, so that's going to cancel. 1 1.5 squared is 2.25. 2.25 times 9, so, well, just 2.25. Okay, and then 10 to the minus 12th squared is 10 to the minus 14th. I'm sorry, 10 to the minus 24th. Times 10 to the 9th is 10 to the minus 15th. Then 10 to the negative 4th on the bottom becomes 10 to the positive 4th on the top, so it becomes 10 to the minus 11 newtons. So this is a tiny force exerted between those two charges, and notice we've got this negative sign. Now this negative sign is included. Now what could it possibly mean? What does the negative sign mean here? Well, one of these charges is pointing to the right, so we call the horizontal alignment here the x-axis, and to the right that's going to be a positive x-going force here and a negative x-going force here. So we've got a positive force and a negative force if you're considering it in terms of the x-axis. But this negative sign, that's not what it means, okay? That negative sign is only telling you that this is an attractive force, okay? Think about it. That negative sign comes up because of the value of either Q1 or Q2, okay? So if Q1 is positive and Q2 is positive, then a positive times a positive is going to give you a positive answer. That'll be a repulsive force. If Q1 is negative, if Q2 is negative, then those are like charges. They would also repel, and a negative times a negative is a positive. So if you have a positive charge, or I'm sorry, a positive force that you get from Coulomb's law, that tells you it's a repulsive force. The two charges are repelling each other. If you get a negative answer, that tells you that it's an attractive force. That's all that the negative sign is telling you. So, and you already know that anyway because they're unlike charges. So there we have it. This equation allows you to find the force between 2 point charges. And that's what Coulomb's law is good for. I think I could do another problem. I think I'll do that. I'll do one more problem where instead of just having two charges affecting each other, let's have three charges affecting each other. So I'm going to erase this. And I'll create a problem where we have three charges involved and we need to find the force exerted on one of those charges due to the other two. So we could do it in a line, which would be one-dimensional, but why do that? Let's try something a little bit slightly more involved. So I'm going to put a charge here, a charge here, and a charge here. So now these will be aligned on the y-axis. These two will be aligned on the x-axis. So this one's right at the origin. So this is the x-axis. Let's say the units are meters here. This is the y-axis. It's also in meters. So these three charges, let's call this one Q1, Q2, and Q3. Okay, they line up on the axes of an XY plane. Let's say the location, this is the origin. This will be, say, 0.3 meters, and this will be 0.2 meters. Okay, so Q1 is 0.2 meters up the y-axis from the origin. Q3 is 0.3 meters to the right of the origin on the x-axis. And what we want to do is we want to solve for the force exerted on Q2 by the other two charges. Now, all of these are like charges. Let's say that they're all filled in. Let's say that this is a 1 micro-coulomb charge. Okay, micro is 10 to the minus 6. Let's see if we can see that. No, you can't. Okay, I've got some glare on the board. So I'm going to write it over here. Mu is from the Greek alphabet, and it represents 10 to the minus 6. So get used to that. In this class, there's all kinds of powers of 10 that we need to be working with here. One single coulomb of charge is a huge amount of charge. And we typically don't end up working problems that have whole numbers of coulombs of charge that we have to deal with. So it's usually relatively small. So 10 to the minus 6, here we have 1 microcoulomb. Let's say this is a 2 microcoulomb charge. And let's say this is a 3 microcoulomb charge. Now these are, you know what, let's make this one a hollow. So this is the one that's going to be a negative charge. Okay, so this Q2 is going to be a negative charge. Q1 and Q3 are going to be positive charges. And we're going to determine what the force is exerted on Q2 due to Q1 and Q3. So now Q2 is negatively charged, Q3 is positively charged. They're unlike charges, so they attract. So the force exerted on Q2 due to Q3 would be exerted in this direction. So I'll draw an arrow connected to Q2 pointing to the right. Okay, and this will be, let's write it over here, F of 2, F of 3 acting on 2. Okay, and then, okay, so this force is the force that Q3 exerts on Q2, Q3 exerts on Q2 to the right. And now there's also an attractive force between Q1 and Q2 because they're unlike charges. So I'll draw that as an arrow oriented in the up y-axis direction because Q1 is positively charged and it's trying to pull Q2, which is negatively charged upward. And we'll call this one F of 1 acting on 2. Okay, so these two forces act together to create yet a third force. And I'll draw that in a different color. So we can add these two vectors together as you add vectors, as we learned about in Physics 1. And this would be the resulting vector. Okay, and this is going to be F2, just F2. So it is a vector. We need to find the angle of it. We can find that angle. And yeah, so here's a good problem. This is what we want to find. We want to find F2. How do we go about doing that? Well, we have to use Coulomb's law twice, once in the x direction, once in the y direction. That's what it comes down to. It's a two-dimensional problem. And remember, a single two-dimensional problem is really two one-dimensional problems. So we can deal with the x direction first and solve for the force exerted in the x direction on Q2. So let's see, that's going to be F of 3 acting on 2. So that's going to be the electrostatic constant, 9 times 10 to the 9th newtons meters squared per coulomb squared. Okay, times the two charges involved. Okay, and I'm not going to include the negative sign. Remember, we talked about what the negative sign means. It means that it's an attractive force between the charges, Q2 and Q3. So we already know the direction is to the right. We've already got that taken care of in the image here. So all we need to do is calculate the size of this force. So we don't need the negative sign there. So it's going to be 2 times 10 to the negative 6th coulombs. Remember, that's what micro means here. And then 3 times 10 to the minus 6th coulombs for the charge of Q3. Now we've done our 1 over 4 pi epsilon sub 0 times Q1, Q2. Now we need to divide by the distance between these two charges, which was 0.3 meters squared. So that's 3 times 10 to the minus 1 meters squared. Now 3 squared is 9, and then 9 over 9, that cancels. So the front number is 2 times 3. That's going to be a 6 out front. And then times 10. 10 to the minus 6 times 10 to the minus 6 is 10 to the minus 12. Times 10 to the positive 9th is 10 to the minus 3rd. And 10 to the minus 1 squared is 10 to the minus 2. 10 to the minus 2 on the bottom becomes 10 to the positive 2 on the top, times 10 to the minus 3rd is 10 to the positive 2, 10 to the minus 3, 10 to the minus 1. Okay? And the units, coulomb squared, cancel with these, coulomb squared, meter squared, cancel with these, meter squared, leaving newtons. Okay, so this is 0.6 newtons. So the force due to Q3 pulling Q2 to the right is 0.6 newtons. So now we found that. We know the value of this force. Now what about the upward force? Well, we can use Coulomb's law again. So the force of 1 acting on 2 is going to be, using Coulomb's law, 9 times 10 to the 9th times 2 times 10 to the minus 6 coulombs times 1 times just 10 to the minus 6 coulombs. And then we divide all of that by the separation distance of 0.3 squared. And remember, the units here are newtons. We've already figured that out from the top one here. So now, once again, the 9 goes away. All the powers are the same. So we end up with 2, because it's 2 times 1 instead of 2 times 3 like it was up here. 2 times 10 to the minus 6, or I'm sorry, minus 1 newtons. So that's equal to 0.2 newtons. So you've got a force pulling it to the right, pulling Q2 to the right of 0.6 newtons. You've got a force pulling upward on Q2 of 0.2 newtons. So now let's go ahead and figure out what the magnitude of F2 is. That's going to be, using the Pythagorean theorem, 0.6 newtons squared plus 0.2 newtons squared, all of that square rooted. Okay, and I need to use a calculator to solve that. And take the square root. And I get 0.632. Just call it 0.63 newtons. Okay, 0.63 newtons. And now the angle that it makes, theta. Okay, what angle does this vector make with the positive going x-axis? Well, we know this side, we know this side, so you can use the tangent equation because you know the opposite, you know the adjacent side. And if you're interested in the angle, you take the inverse tangent of the opposite over the adjacent, so that would be 0.2 newtons divided by 0.6 newtons. So that's the inverse tangent of 1/3. So let's figure out what the inverse tangent of 1/3 is. So let's see, inverse tan. I get 18.4 degrees. Okay, so we solve for the size and the direction of the force. It is a vector quantity, so if I was asking for something like this on a test or a quiz, you would definitely have to provide both the direction and the size of the force if you're going to be correct. So we went right ahead and we did a one-dimensional Coulomb's law problem. Now we've done a two-dimensional Coulomb's law problem, which is, remember, is just two one-dimensional problems put together. So, and that's the use of Coulomb's law. Now, if you were given the mass of Q2, then you would be able to determine now what its initial acceleration was at this instant in time. So guess what? Knowing the force, remember, F equals ma, that allows you to determine acceleration, and that eventually allows you to determine the projected path of this thing. Okay, where would it be? How fast would it be moving at any particular point in time? At what rate would its velocity be changing? What direction would it be heading? All of those things are predictable if we know the force. So that's a good example. A couple of examples of Coulomb's law. I'm going to go ahead and stop now.